realization of Picard motives and applications.
Thank you, Florian. I'd like to start by thanking the organizers for inviting me to spend time at the Newton Institute. It's a great pleasure to be here and for giving me the opportunity to give this talk as well. Well, the other day Andrew Wiles was saying how he felt overwhelmed speaking in this room. I would like you to please take a moment and try to imagine how I feel giving this lecture in this room. Anyway, so I'm going to report on ongoing joint work with my collaborator from Munich, Cornelius Greiter. When we started working on this project, Cornelius and I have had different goals in mind. I was really interested in proving an equivariant main conjecture in Iwasawa theory, which by Iwasawa codescent would imply some classical conjectures on special values of global Artin L functions. And the conjectures I had in mind, so there were several. I'm not going to talk about all of them today, but the conjectures I had in mind were pretty much the following: the Brumer-Stark conjecture, the Cotes-Sinnott conjecture, and then, so these I will talk about today. I'll cover these two somewhat in detail. But I was also interested in the Rubin-Stark conjecture, which is an integral refinement of the abelian Stark conjectures for L functions of arbitrary order of vanishing at s equals 0. And also a conjecture of Dick Gross, which can be viewed as a p-adic refinement of the Rubin-Stark conjecture. And secretly, I was hoping that I could say something about the equivariant Tamagawa number conjecture for Artin motives with abelian coefficients. So these were my motivations. Cornelius came on board with different motivations. So he simply wanted to compute explicitly fitting ideals over various group rings, sometimes profinite group rings, of objects of arithmetic interest, various Iwasawa modules, ideal class groups, for example, étale cohomology groups at the finite level. So once we got together and started working together on this project, so by the way, my title may not reflect the fact that my talk is about special values of L functions, but that's what it is about. This machinery of Picard 1 motives will be used in order to attack these problems. Yeah. So my ultimate goal is to talk about special values of L functions. So once Cornelius and I got together and started working together on this project, of course, our lists of goals merged, and we worked together on both this type of conjectures and on computing fitting ideals. So in this talk, I'll mainly talk about these two. If there is time towards the very end, I can perhaps tell you what I can say about the equivariant Tamagawa number conjecture for Artin motives with abelian coefficients as well. Okay, so let me just set the notations.
Christian, can I ask you a question?
Yeah.
I've always thought that the first two are equivalent, knowing them for all the way up the cyclotonic ZT extension.
Brumer-Stark and Cotes-Sinnott, you mean? No.
Well, once you have a description of K
Trivial zero.
Sorry?
Trivial zero.
Trivial zero.
Exactly. Yeah.
This nightmare. Yes.
There are issues. Yes. Got it. Okay. So I'll just set the notations. I'm just going to state these two conjectures. I'll state them in an unusual form because I want the statements to fit with the machinery of Picard 1 motives. So I'm just going to, in passing, tell you how the statements I'm going to give you are equivalent to the classical statements you may be used to. So throughout, capital K over little k will denote an abelian extension of global fields of arbitrary characteristics. And so I am going to, in the base field, I'm going to fix two sets of primes, S and T, sets of primes, finite, satisfying the following properties. So I want S to contain S infinity and S ramified. Of course, in the function field case, S infinity is empty. I want T to be disjoint from S. And I want T to be chosen so that there are no roots of unity in capital K congruent to 1 mod all the primes in capital K sitting above primes in T. Yeah? So for example, in function fields, you can just take T to be a non-empty set. That would do. In number fields, it's safer to work with T consisting of at least 2 primes of different residual characteristics. That would do. Yeah? So once we have these, then one can associate to this set of data an equivariant global L function, which I'm going to denote like this. So this is put together as follows. So it's the product of the usual equivariant L function. So you take a sum for all the characters of G. G is abelian. Yeah? Of the S incomplete classical L function associated to the character chi times the idempotent associated to chi inverse in the complex group ring. And then you multiply this by the following product. So this is a product with respect to primes in T of 1 minus sigma V inverse. So this is the Frobenius associated to V in G times the norm of V to the power 1 minus S. And I'm going to denote this quantity over here. So this is a holomorphic function in S. And I'm going to denote that by delta sub T of S. Okay? And now I'll tell you a little bit more about this delta sub T of S later. So it turns out that this function could be thought of as a holomorphic function. So this is holomorphic everywhere. But it, of course, it takes values in the complex group rings C bracket G. Yeah. Okay? And now here is a very important property of this function. So this is a deep theorem. In number fields, this is due to Derlin-Ribet, Kasuno-Guess, and Barsky independently. And in function fields, this is essentially due to Derlin and Tate. But I have to say that the proof in function fields is much, much, much easier than the one in number fields. So this is simply telling you that if you are trying to evaluate this function, which you can evaluate anywhere on the complex plane, at negative integers, so I'm going to take n in Z greater than or equal to 1, and I am evaluating it at 1 minus n, then this is in Z bracket G. Okay? All right. So the first two conjectures that I'm going to talk about, so these Brumer, Stark, and Coates-Sinnott conjectures, say something about these special values, about the special values of theta at non-positive integers. Yeah? And so let me describe the Brumer-Stark conjecture. Again, I'm going to state it in a rather unusual form, but this is equivalent to the classical formulation. So for that, I'm going to introduce a modified ideal class group, which associated to the top field capital K, which I'll denote by C sub t. Yeah. So C sub t, so if I am talking about number fields, so if the characteristic of little k is 0, so number fields, this is going to be what? This is going to be the quotient between the group of fractional ideals in capital K, which are coprime to t. Yeah, so this is a group in capital K, this is a subgroup of the group of fractional ideals in capital K. And I'm going to mod it out by the principal fractional ideals, so F, OK, which have generators, F, which are congruent to 1 modulo W for all W in Tk. You have to realize that this surjects into the classical ideal class group. Yeah? It's a bit larger. Yeah? Of course, in function fields, so if the characteristic is p greater than 0, you can imagine what this is. So perhaps a more appropriate notation for this thing would be pick 0 of k sub t. Yeah? So these are what? These are divisors of degree 0 in K, supported away from T. Mod out by principal divisors associated to functions which are congruent to 1 mod W for all W, in Tk. Okay? Of course, this surjects onto the classical Picard group of divisors of degree 0. Yeah? Okay. And now I'm ready to state the first conjecture. So the statement is the following. So conjecture, Brumer-Stark. So this is a conjecture about the value of theta at 0. So you take n equals 1 in here. So theta sub s gamma t of 0 belongs to the annihilator over z bracket g of Ct. Yeah? So I have to make a comment here. I'm slightly lying. This is not quite equivalent to the classical Brumer-Stark conjecture. It is equivalent to it in characteristic P. In characteristic 0, it's equivalent to it away from the two primary part of your ideal class group. I won't be able to say anything about the two primary part of this conjecture. So in other words, if you want to annihilate the 2 silo subgroup of this guy, I won't be able to say anything about it. So for our purposes, this is equivalent to the classical Brumer-Stark conjecture. Yeah? Okay? All right. So that, yeah.
Why is the value even? Why are the coefficients even rational, let alone integral?
That's a theorem of Siegel. So even if you stay away, yes. Let me explain that. Okay, because this delta sub t, it's a bit strange. So let me explain what delta sub t is. Remark. Actually, this is a lemma due to you. So remark, what is delta sub t evaluated as 1 minus n? This is inside, so this is John Coates' lemma, in the annihilator of ZL bracket G of H1 et al. Of OKS, so these are the S integers in the top field, with coefficients in ZL of n, torsion. I remind you what this is. So this is QL mod ZL, twisted alatate n times, fixed by the absolute Galois group. As a matter of fact, so the lemma I'm referring to is simply saying that this annihilator is generated by these guys for all t and for all n. Yeah. So now, for example, at 0, you are going to get the delta sub t of 0. That's in the annihilator of the group of roots of unity. You hit that, you get the classical Stickelberger guy. At negative integers.
Sorry, yeah, I was.
Yeah. No. But
I think s equals 1. I would have thought Brommer-Stark was about s equals 1.
I'm not talking s equals 1. I'm talking s equals 0, minus 1, minus 2.
Ah, I see.
Yeah, my normalization, this 1 minus n, it's done so that when I say the... Yeah.
No, somehow I always think of Brommer-Stark as being s equals 1. I mean, Stark being as s equals 1.
We've moved it to 0 a long time ago. Since John Tate wrote his book, it's at 0 now. It's equivalent to the original formulation of Stark at s equals 1 via the functional equation. Yeah, but we work at s equals 0 now. Yeah. Okay, so this is Brommer-Stark, and then I'm ready to state the Cotes-Sinnott conjecture as well. So conjecture, Cotes-Sinnott. Now, I forgot to say that in order to simplify matters, so this is not necessary, but in order to simplify matters, if my fields are number fields, I want the top field to be a CM field, and I want the bottom field to be totally real. Now, okay? So now, the Cotes-Sinnott conjecture simply says something about the values of this theta at truly negative integers. So I'm making n strictly greater than 1 now. So for all n strictly greater than 1, theta at 1 minus n should annihilate. So the following étale cohomology group. So this is over ZL bracket G now. I'm fixing an L prime. Okay. H2 et al. Off. And now I'm going to put this ring of S integers, but with a prime, and I'll explain what the prime means in a moment, with coefficients in ZL of n. So this should happen for all L prime, for all n greater than 1. Okay? What is this OKS prime in characteristic P? It's easy. This is just the ring of S integers upstairs. Yeah? In characteristic 0, this is the ring of S integers in the plus subfield, so this is the maximal totally real subfield of capital K, with the primes above L inverted. Yeah? That's how it goes. All right? So this is the Cotes-Sinnott conjecture. Of course, I have to mention a few things. So this is not the original formulation of the Cotes-Sinnott conjecture, because that was formulated, first of all, only in characteristic 0. And in that situation, it was formulated in terms of Quillen K groups. I am dealing with an étale version, étale cohomological version of the Cotes-Sinnott conjecture. However, if the Quillen-Lichtenbaum conjecture is true, then the two formulations are equivalent. Unfortunately, Quillen K theory doesn't pop up naturally in Iwasawa theory, so this is why I can't say anything about the K-theoretic version. Unless these people in Princeton will tell us in a few weeks that they have a manuscript and we can check the proofs. Apparently, there is a proof of the Quillen-Lichtenbaum conjecture now, but yeah, okay, so this is the one I'm going to deal with. Okay, and now, so now I'm going to shift gears quite a bit. I'm just going to move to an algebraic geometric context, and I'm going to talk about these Picard 1 motives. Yeah? So p-adic realisations of Picard 1 motives. So here is the context. I work over an arbitrary algebraically closed field, which I denote by kappa. So kappa is an algebraically closed field. Any characteristic, any kind of field you want, closed field. And I'm going to take two smooth projective curves over this field. So x and y are smooth projective curves. For simplicity, I'm going to assume that they are connected. Not necessary. So over kappa. And they come in a Galois cover like this, Galois group G, but throughout part 2 of my talk, G does not have to be abelian. Not necessarily abelian. Yeah? And now I'm going to play sort of the same game I played before with these curves. So I'm just going to pick S and T, two disjoint, not necessarily non-empty set of primes in Y. So these are sets, finite sets of closed points in Y, in the base curve. Okay? And now, to this type of data, is it okay if I write on this board? Can everybody see this? Yeah? So, to this type of data, x over y, no, let me say x, and now I'll denote by sx and tx, the sets of closed points in the top curve sitting above points in S and T respectively. Deligne associates a one motive. I'll explain in just a moment what that is. So this is Picard one motive, which I'll denote like that. And what does this consist of? Well, it consists of the following type of data. So you have a morphism between a lattice. So this is LS is simply the set of divisors of degree 0, or the group of divisors of degree 0 supported above Sx. So this is a free Z module of finite rank. Yeah? And then J sub T. It's a semi-abelian variety. It's simply the generalized Jacobian associated to the curve X and the set T. So this is a generalized Jacobian. So it's an extension of the classical Jacobian J of X by a torus, which depends only on T. Now, let me pause here for a moment and just describe the kappa rational points of this guy. That's all you need to know about. JT kappa. And so this description will tell you that I haven't completely gone mad. I'm not too far from this context, okay? So this is divisors of degree 0, yeah, on X away from Tx, mod out by the group of principal divisors associated to functions on X, such that if you evaluate these functions at all the points in Tx, you get 1. Yeah? So that's the kappa rational points of this semi-abelian variety. And now, what is delta? Delta is simply the divisor map, divisor class map. Yeah? So you get a morphism. Of course, due to the fact that you're talking about Sx and Tx, which are G equivariant, this morphism would be a morphism of Z bracket G modules. Yeah, you should think of them as Z bracket G modules. You know, whenever you have such a thing, yeah, so you take a prime L, prime, including L equal to the possibly non-zero characteristic of the field kappa, you associate to that, so this is Deline's construction, you associate to that a module which is L divisible of finite corank, and as a consequence, so I'm not going to describe this construction for you, this is Deline's formalism. So as a consequence, you can come up with an l-adic realization in the usual manner. So this is the l-adic Tate module associated to the one motive, and it's also, I'm going to refer to it as the l-adic realization for every prime L. This is naturally a ZL bracket G module. It's finitely generated over ZL bracket G, and it's free as a ZL module. You don't really need to know what this looks like, but you need to know the following thing. The following thing is essential in what follows. So this guy is the middle term of a sequence, an exact sequence in the category of ZL bracket G modules. So the middle term is this l-adic realization of your one motive. Yeah? The right-hand side is the lattice tensor ZL, and the left-hand side is the l-adic realization, the usual l-adic realization of your semi-abelian variety, JT. Okay? Now, let me denote this by star. So this happens for every L. And I have to tell you something. So unless G is trivial, if you think of this as representing a class in X1 over ZL bracket G, it's never the trivial class. Actually, understanding this class, my efforts to understand this extension class led me to applications to the equivariant Tamagawa number conjecture. I'm not going to really talk about that. But the extension class of this sequence, it's extremely important. Okay? All right. So, so let me tell you what Cornelius and I have proved as far as these one motives are concerned. So again, we are not in a number theoretic situation here. I mean, my kappa can be anything, G can be anything, not necessarily abelian. And so here is theorem 1. If S contains the ramified locus of the cover and T is non-empty, then this l-adic realization is always ZL bracket G projective for all L, including L equal to the possibly non-zero characteristic of the field kappa. Okay. For those of you who are familiar with this type of result, so for example, I mean, there is a well-known paper of Nakajima, 1980s, dealing with the Galois module structure of certain spaces of differentials fixed by a Cartier operator in characteristic P. That is a particular case of this theorem. So if you restrict this theorem to L equals P equal to the characteristic, so characteristic greater than 0, then Nakajima's theorem is a corollary of that. Okay? Okay, so that's the theorem. You know, so this is geometric. I want to restrict this theorem to see what we can do with this theorem in a more number theoretic setting. Okay? So now I'm just going to move.
I'm sorry.
Yeah.
Just back to one thing was, what did you say about the non-triviality
of this extension class? So X1, if you view this guy in X1 over ZL bracket G of this by that,
right.
It's never trivial. So in other words, this is not a split sequence as a ZL bracket G module sequence.
What if even if S is something from S is the difference of 2 points that are prime to L torsion or something of this sort, this is not trivial?
No, 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 no. No, S under S containing S ramified and T non-empty. This is what I'm talking about, right? So I'm imposing those conditions. Yeah, it's not trivial.
Maybe that
it has something to do with the fundamental class in global class field theory.
Yeah, but somehow, I mean, this is, I mean, when S is just a difference of 2 points, this is just some Kummer extension. I mean, the extension of the trivial motive by T.
It's a bit more complicated than that. We can talk about, I'm not going to use that in the talk. So that will lead to the ETNC conversations.
Oh, maybe it's because of this ZLG thing.
It's never trivial.
Now, one other question I
yeah.
For this, you really need T to be non-empty?
Yeah, absolutely. If T is empty, then you don't get cohomological triviality. It's not G cohomologically trivial, unless G is...
I see.
Yeah.
So the Tate, the Tate module of X itself...
no, that's very rarely cohomologically trivial. No, this is the whole purpose of working with these guys rather than the classical p-adic realizations of Jacobians or generalized Jacobians. Those are not enough.
But this is a very tricky factor.
It is. It is. I mean, it takes a while to prove this thing. Yeah. Okay, 3. So I'm just going to restrict this geometric thing to the characteristic P global field situation. So the question I'm going to ask, so this is function fields now. The question I'm going to ask is, what happens if this set of data cover G, S, and T is defined over a finite field? I'll explain in just a moment what I mean by that.
Oh, I think that, yeah, sorry.
Over FQ, Q is some power of P, where P is prime. Okay? So let me explain what we can say in that situation. We can say much more in that situation, and that will lead to the applications we had in mind. So first of all, what do I mean by defined over a finite field? I mean, so it should be pretty clear. So what this means is the following. So you have two smooth projective curves over the spectrum of FQ, yeah, x naught, y naught. This is G, yeah. And then you obtain x, y by simply going up to the base changing to the algebraic closure of FQ, yeah. So you get y here, you get x, same thing. For simplicity, I'm going to assume that x naught, y naught are geometrically connected. So assume, in other words, when we do base change, then we get connected curves over the spectrum of FQ bar. Well, at the level of fields, so by the way, what are the sets S and T? Well, you can start with an S and T here in y naught, and then the S and T in y that the theorem is talking about are simply the set of points, close points in y, sitting above points in S and T in y naught. Okay? So then, at the level of fields, what do I have? So I have this extension of global fields corresponding to x naught over y naught, FQ bar. Okay, and then this is, let me denote this by k infinity. I'm just going to trick you into thinking in terms of Iwasawa theory now. So this k infinity is kfq bar. Yeah. Fortunately, this gamma, which is the Galois group of this extension, is not quite ZL or ZP as in Iwasawa theory. This is really Z hat, but we'll take it as it comes. And this is k infinity. Again, the compositum, but due to this connectedness hypothesis, this is a perfect diagram. So if I denote by script G the Galois group of that extension, k infinity over little k, then script G is isomorphic to G cross gamma. Okay? And now let me assume from now on that G is abelian. Yeah? Then I'm just going to play the game we play in Iwasawa theory. So what I do is I'm going to look in this tower, k up to k infinity. For every n, there is a kn, yeah, of degree, unique kn of degree n over capital K. I'm going to denote by, say, Gn, this Galois group. Yeah? And inside this Gn, I have, so this is associated, I have a function like theta sub s gamma t. This is associated to st and this extension. You evaluate it at 0. You end up in this group ring. Okay? Now, these are well behaved with respect to Galois restriction maps. So you are entitled to take the projective limit of these guys with respect to the Galois restriction maps. So what you get is a theta infinity s gamma t, which is just the projective limit of these guys. Evaluated at 0. Where does that live? Well, it lives in the projective limit of these group rings, which is z double bracket script g. In fact, you can show that in function fields, this entire construction is really unnecessary, but I want to do it just the way we do it in number fields. So not only is it unnecessary, it turns out that you actually end up in the usual group algebra, ZG. Yeah? Okay, so you should think of this as the function field analog of an equivariant l-adic L function. Right? And here is the next theorem. Okay? Here is the next theorem. Theorem 2. Yeah. Look, so I am assuming that G is abelian. It turns out that this l-adic realization of the Deligne Picard 1 motive associated to that set of data has a finite presentation over this ring, ZL double bracket script G for all L, so it's finitely presented. By the way, this ring is non-Noetherian due to the Z hat thing. Nevertheless, this is finitely presented, so you can talk about its fitting ideal. Okay? So for all L, we compute this fitting ideal. And it turns out, of course, to be principal and generated by this state T. Yeah, so what is the input here that we need? I mean, we need some hard calculation here that links these guys to L functions. And for L different from P, that input is a theorem due to Deligne and Tate. Which simply relate the L function at the finite level to a certain determinant. So this is the determinant over QL bracket G of 1 minus. And now, look, unlike number fields, you have a canonical generator here, and this is the Q power geometry, arithmetic Frobenius gamma. Okay? So you take the action of this arithmetic Frobenius times Q to the power minus S. Remember, you live over FQ, acting on this l-adic realization of the one motive, tensored QL. So this is for all L different from P. Yeah? Okay, so this to us is like a main conjecture away from the characteristic. Now, of course, we claim to have proved this at the characteristic as well. This is not good. By the way, this equality would never hold with L replaced by P. I mean, this L-adic realization, the p-adic realization is too small to give you the actual L function. So there we have to do some work. I'm not going to get into details. So we are using crystalline realizations. And then we are using the theorem of Bloch and Illuzy, which tells you how the p-adic et al. Realization sits inside the crystalline realization.
The previous p-adic you meant T sub P.
T sub P, that's my p-adic et al. Realization, yeah. Yeah. Okay. So you can think of these L-adic realizations as L-adic et al. Homology groups of M. Yeah. So we have that. Let me give you the consequences. Okay? So let me show how this theorem, theorem number 2, implies Brumer-Stark and code-Sinnott, for example.
Oh, sorry, just one question about this again. So that determinant will be just the product of the two determinants on either side, right?
Oh yeah, yeah. If you tensor with QL, of course, I mean everybody becomes split over QL bracket G. Exactly, and that's how you put that together. That's why how you identify this guy. Plus the Lefschetz trace formula satisfied by the L-adic et al. Cohomology and so forth. That's how that theorem is proved. It's not hard. No, proving this is not so hard. Okay. Okay. So now applications. Brumer-Stark. I'm just going to prove a refinement of Brumer-Stark. So refine. Remember, we are still in characteristic P. I'll move to characteristic 0 shortly. So I'll try to mimic this machinery in characteristic 0. Of course, the one motive doesn't exist. But in the end, you don't need the one motive. You just need some Iwasawa modules that behave exactly like the L-adic realizations of the one motive.
As always.
Yeah, and this is the game Iwasawa played originally with the Jacobian and its L-adic realizations. Here, we need something extra, yeah, a little bit more information. So, refine Brumer-Stark. So, let me just prove the classical Brumer-Stark really quickly for you. So, look, you have this exact sequence. Yeah? You know that your theta infinity lives in the fitting ideal over the big group ring, the profinite group ring of the term in the middle. That fitting ideal is inside the annihilator of the guy to the left, just the annihilator. The fitting ideal does not behave well with respect to inclusions, unfortunately. So this is in the annihilator of PL of JT over the big group ring. This is for all L. I'm working L-adically, but if I cover the conjecture for all L, then I'm done with the whole thing. And now, what do? I project down to the finite level. So I take gamma coinvariance. That was my dream all along. So what do I get? I get annihilators over the finite group ring. Yeah? Now, due to the way this theta infinity was constructed, when you take gamma coinvariance here, you actually get the finite level gamma at 0, theta at 0. And now what happens is this. It's very easy to see that the gamma coinvariance of this guy is really my CT at the finite level, this modified ideal class group, tensor ZL as a ZL bracket G module. Done. So that would be Brumer-Stark. We do a bit more. So here is a question that people have been asking for at least 20 years. Look, you do have this theta in the annihilator. Is it in the fitting ideal? Does this belong to the fitting ideal over ZL bracket G of this CT? Okay? The fitting ideal is smaller than the annihilator. this argument could not have led me to the fitting ideal because of the way fitting ideals behave with respect to inclusions, misbehave with respect to inclusions, okay? So the answer to this question is no. I've known this for quite some time. You can check out, I have a Compositio Mathematica paper published in 2004 in which I give an infinite class of counterexamples. But at the time, I didn't understand why I had those counterexamples. So let me tell you the actual fitting ideal related property. So theorem, so this would be the refined Blumer-Stark. In fact, we show that this theta belongs to the fitting ideal of the Pontryagin dual of CT tensor ZL. So this is home into QL mod ZL for all M. Okay? Actually, we compute this fitting. This was Cornelius's dream all along, to compute fitting ideals concretely. And we compute this fitting ideal, and this turns out to be the Synod-Kurihara ideal. So this is a generalization of the classical Stickelberger ideal, is obtained by fattening up Stickelberger ideals at the intermediate levels in this extension. So actually, the theorem should say this, Synod-Kurihara ideal. Of course, in our case, this is t modified, so there is a t involved. Yeah? So we compute that. So of course, I mean, this is inside the annihilator over ZL bracket G of CT tensor ZL. That would be the classical Blumer-Stark. This is the refined Blumer-Stark. Yeah? Okay. Cotes-Sinnott.
Oh, sorry.
Yes.
Before you do that, just
Yeah.
a question about your theorem. So, if I understand correctly,
Please.
Your conclusion here is, of course, about the generalized Jacobian, but this projectivity of this extension is playing a key role in your approach.
No. So the projectivity of TL of M sub S gamma T plays a key role in computing this fitting
That's
ideal.
what I mean.
Absolutely,
So
absolutely. Theorem 1 combined with Dulin-Tate and Blachy-Luzy plus some extra stuff implies theorem 2.
Right. So somehow this, considering this extension is playing a key role in getting at the annihilator of the generalized Jacobian.
Absolutely, absolutely.
So this is the thing that naively doesn't exist over a number of fields. I mean, the generalized Jacobian.
But you will see that it does.
Yeah.
You will see that it actually does exist. Okay, Cotes-Sinnott. So for Cotes-Sinnott, we have to play a slightly more dirty game. So it's not only gamma coinvariance, of course, it's twists plus gamma coinvariance. So what does that entail? Well, let me tell you something about twisting inside the group ring, if you haven't seen this. I'm sure you have. Yeah, so there are twisting maps for every M, which take a G inside G into G times the cyclotomic character to the nth power of G. Yeah, so this is a twisting map. And here is a property. So if you have a ZL bracket G mod M, say, and you want to compute the fitting ideal over ZL bracket G of M, say, twisted M times, then it's easy to see that that's the twist that way minus M of the classical fitting ideal of M. That's one property. And then the other property that plays a very important role is the following. Remember, Cotes-Sinnott is about these values. How do you get these values from theta infinity, which is constructed out of values at 0? Well, it turns out, so this is a fact, Iwasawa theorists will have no problem believing this, Yeah? Okay. So let's apply all this stuff, see what we get. So I'm going to play now with that sequence. Yeah? So now I'm using theorem 2, which simply gives me the fact that theta infinity is in the fitting ideal of this guy. Yeah? And what this machinery is telling me is that theta st at 1 minus n will be in the fitting ideal over ZL bracket G of the twist of the l-adic realization of M n minus 1 times Galois. Yeah? Okay. How do we get to étale cohomology from here? We have to get rid of T, for example. Have to keep only S and so forth. So here another important ingredient due to Deligne comes in. There is a duality pairing between the l-adic realization of this one motive and the l-adic realization of the dual one motive, which would be called the Albanese one motive. That would not be really appropriate here because the abelian variety involved in the construction of this one motive is self-dual. It's a Jacobian. So you get a Picard one motive. What is it? Is M sub Ts, just naively. So this duality pairing, it's a perfect duality pairing, leads to an isomorphism between this guy and TL of MTS. So this is the dual one motive. Yeah? And now I'm going to take star, which simply means hom over ZL into ZL. So that's the usual dual of a free ZL module. Yeah? Twisted a la Tate once. Okay?
Sorry, I got confused by what you said. This Jacobian is a generalized Jacobian, so it wouldn't be self-dual.
No, I'm really talking about the Jacobian itself. You see, what happens when you take the dual of a one motive, so you have a Jacobian, extend that by a torus, and then you add a lattice in.
Right.
When you take duality, then the lattice changes roles with the torus.
You get the character.
Exactly, yeah. And the abelian variety involved changes roles with its dual.
Right.
In this case, the abelian variety is just a Jacobian, which is self-dual. So the Jacobian stays in. The generalized Jacobian changes to J sub S. J sub T becomes J sub S, right?
I guess I see that.
Okay. As a matter of fact, J sub S will show up in just a moment. Okay, so we have this fitting ideal, right? So let's start twisting here. I'm just going to replace TL of M sub S comma T by this guy. What do we get? We get the fitting ideal over ZL bracket G of TL sub MTS, okay, star. Now, n minus 1 plus 1 is n, gamma. Yeah? Now, let me explain something. So from this sequence, I mean, if you write the same sequence for S and T swapped, you are going to get a surjection from TL of MTS star. I'm taking duals. And these are duals over ZL, so the sequence will stay exact. Surjects into this guy, the generalized Jacobian, the new generalized Jacobian. So this is a surjection. Fitting ideals behave nicely with respect to surjections. So this is inside the fitting ideal ZL bracket G inside TL JS star and Galois. Okay? Now, this is H2 et al. Why? Well, let me just give you a reason, because there is an et al. Fundamental group showing up here. I thought I would say fundamental group at least once in this talk. So this is really isomorphic, if you think about it, to the Pontryagin dual. Now, Pontryagin dual. So what do? You take TL of JS You twist it minus n times. You take gamma coinvariance. Now, you apply the Riemann hypothesis in function fields, and you will realize that this is finite. And then you take the Pontryagin dual, home into QL mod ZL. That's isomorphic to H2 et al. Of OKS with coefficients in ZL of n. Why am I saying this? Well, you shouldn't be shocked by this. TL of JS is a quotient of pi 1 et al. Of a certain scheme. It's the maximal pro-L abelian quotient of pi 1 et al. Of OKS, if you want. I'm sorry, the closure of OKS in the big curve X. You go all the way up.
The fitting idea, that thing is co-invariance on the outside of gamma. So
yeah, I'm playing very dirty games here, but everything is correct. So due to the fact that when you take this guy, so this is a free ZL module, right?
Right.
When you take gamma invariance, you get nothing.
Right.
When you take gamma coinvariance, you get something finite. Right. So you can move things around. I'll show you the argument. It involves some X functors and so forth. It's not straightforward. Okay? So that's H2 et al. So we are getting cosinus, but in fact we are getting refined cosinus in the sense that theta at 1 minus n is in the fitting ideal of H2 et al. We can all actually compute the full fitting ideal. Cornelius's dream. To come up with a full description of the fitting ideal. So that's a fattened up version of the classical sort of higher Stickelberger ideal associated with 1 minus n. You know, Kurihara has defined all these things. It so happens that we just get them on the nose here. Yeah. So yeah. So although the naive the naive refinement of Brumer-Stark is not true, the naive refinement of cosinus is true. And that comes from the fact that these generalized Jacobians, which do lead to et al. Cohomology groups, after twisting and taking duals, sit on the right side of these exact sequences. And fitting ideals behave nicely with respect to inclusions, to projections. Okay? Number fields. Sorry. So why did I go through this exercise so carefully? Well, two reasons. I wanted you to realize two things. Once you have a module, like the p-adic realisations of the one motive, which satisfies the following properties. So first of all, it fits into an exact sequence like this, which via twists and co-descent leads to the classical objects we are after, ideal class groups, et al. Cohomology groups, and so forth. Plus, it satisfies theorem 1, which is ZL bracket G projectiveness, and it satisfies theorem 2, which is, we think of theorem 2 as an equivariant main conjecture in the abelian setting. Then everything else is just a formality. You just feed it through this machine, and you get exactly what we got here. I mean, refined cosinus, refined Brumer-Stark, for example. Yeah? So the only thing I have to do in number fields is to invent such a module, cook up an Iwasawa module, which satisfies all these properties. Okay? Of course, I don't have the one motive, but I don't need the one motive. I just need the p-adic realisations. Yeah? So let me tell you what we get in number fields. Let me just erase here. I'm sorry, I may go over time by 5 minutes. I apologize. I didn't plan very well. I can always blame it on the room. There is a lot of pressure on me here. So.
Pressure usually makes people go faster.
I slow down. Okay, number fields.
We asked a lot of questions.
No, but that's good. Thank you very much. I haven't actually faced an audience including arithmetic algebraic geometry, so I'm really happy that. Okay, so in number fields. Let me tell you the assumptions we are working under. So we don't have clean results, of course. I mean, we are working under some assumptions. Again, K is Cm. Little k is totally real. unnecessary, but there are theorems out there which simply say, well, if you stay away from the two primary part of these ideal class groups, then it's enough to prove, for example, Brumer-Stark for this situation. This is a theorem due to Tong-Kai-Yang. So I'm going to do that. Of course, I cannot say anything at L equals 2 because we need an input, which is the main conjecture due to Andrew Wiles. And we don't know that at L equals 2 at this level of generality. And there are other reasons why I am assuming that this prime, so fix a prime, greater than 2. Okay? And now I'm going to assume some other things. This is necessary as an assumption. I cannot say anything at L equals 2. There is another necessary assumption. I'm going to assume that the Iwasawa mu invariant associated to K and L is 0. This is a big conjecture in Iwasawa theory, so that's again necessary. Our techniques break down. Please note that in function fields, all these modules are ZL free, so the mu invariants are 0, automatic. Okay? You know, some unnecessary conditions, but I'll make them anyway. I'll impose them anyway because I want this to be as simple as possible. I want the root of unity of order L to be in K. Yeah. And what else? A necessary assumption. I want SL to be in S. SL is the set of primes above L. Okay? So this is necessary, unfortunately. Right? Okay? You know, so I play the same game as before. Of course, K infinity is simply going to be the cyclotomic ZL extension. Cyclo. Yeah? And again, an unnecessary assumption, but I'll make it anyway. I want this to be disjoint, linearly disjoint over little k with capital K. Yeah? So that would lead to a situation just like before. So I have a K infinity here, which is just a compositum. This is my script G. And of course, script G is isomorphic to G cross gamma. Yeah? So what do? I want to construct this module, TL. Okay? So let's think about how Dulin constructed his. So he started with a map, this delta, which is a divisor map, between a lattice of divisors and the kappa rational points of a semi-abelian variety, and then there is a machinery that associates to such a map an L-divisible group of finite co-rank, and then to that you associate the p-adic realization. So I'll have to tell you what this map is. So what this is, what that is, what the map is, and then you feed everything through Dulin's machinery, and you get your TL of M sub S gamma T. What's the map? So here is what I'm going to do. Of course, so there is a Kn here, natural, yeah? And at every level n, I'm just going to construct, so take this CT, you know this generalized ideal class group, level n, tensor it with ZL, take the minus part. Yeah? And take the injective limit of these guys as n goes up to plus infinity. Yeah? That's it. So this will play the role of the L primary part of the kappa rational points of my semi-abelian variety. L primary part. Yeah? Now, what is LS? That's easy to figure out. So those are divisors, not of degree 0. You will see that that's not necessary. At the infinite level, in K infinity, supported on S, but let me put an infinity there, up. Yeah? But away from SL infinity. Tensor this with ZL. Take the minus part. If I take the minus part, whether I take divisors of degree 0 or not, it doesn't matter. Minus part coincide. Yeah. Please note that once I take the minus part, the divisors supported at the infinite primes, I have infinite primes that I have to worry about, are not there anymore. Yeah? So by the way, what do I mean by the minus part? Of course, most of you understood that, but this is CM. There is a unique complex conjugation guy. I'm taking the eigenspace on which J, this complex conjugation, acts as minus 1. I can do that because I'm tensoring with ZL and L is odd. Right? And then, if you think about it, not too long, I mean, this is easy. There is a divisor map. That's my data. Now I feed this data through Deline's machinery, which produces for me a divisible L group of finite corank. And then I apply the usual procedure, and I'm getting that. I want to emphasize, so this automatically lives on the minus side of things, but just for emphasis, I want to put a minus there. Yeah? Theorems. So I'm sorry, I should have showed you how Deline, it's a very clever construction, how he comes up with this L divisible group, but that would have not been possible. I'm already over time, big time. So, okay, theorem 1. It's what you expect. CL is ZL bracket G projective. Okay. I really want to emphasize that S contains SL and the mu invariant is 0. These are our assumptions. Without these assumptions, we can't do anything. Huh? Theorem 2.
You need this new add only for big large.
I'm sorry.
Do this, you need the vanishing of the mu only for.
Oh, well, for example, if the vanish of the mu doesn't happen, then this is not ZL free. It's not going to be ZL bracket G projective.
Only for large K, not for all you.
No, only for capital K. But that's enough. That's a strong condition. Yeah. So over Q, for example, if we are abelian over Q, we are okay, and so forth. But no, that's a serious assumption. Theorem 2. Of course, you have a theta infinity. Yeah, you do the same thing as I did in function fields. That theta infinity is a genuine equivariant L-adic function here. So fitting over, I have to be careful here. So since my guys live on the minus side and I want to get the fitting ideal on the nose, I have to work on the minus side of the group. Is generated by theta infinity. What's the input here? I mean, remember, in order to get theorem 2 from theorem 1 in function fields, I needed the Dulin-Tate theorem, the main conjecture, plus some extra at L equals P, right? The input here is the main conjecture in number fields due to under 1. Again, L equals P here is L equals 2, and I can't do anything at L equals 2 because we don't have this thing. We have it over Q, billion extensions of Q, right? L equals 2. You proved that in the 1990 paper, I think. Yeah. Unfortunately, I can't really use that because I still want to split my spaces into plus and minus in a clean way. So I haven't thought about that yet. Yeah. Okay. You know, corollaries, everything from now on is just formal. It follows from. Yeah. So let me just give you the theorems. So theorem 1. refined, unfortunately imprimitive Grummer-Stark. So what have we got? If SL is in S, L is odd, and the mu invariant is 0, these are the assumptions. I really want to emphasize that we cannot prove a clean theorem here. Then theta at the finite level, at 0, is in the fitting ideal over ZL bracket G of CT tends towards ZL minus Pontryagin dual. This is the refined version, yeah, which is, of course, inside the annihilator of CT tends towards ZL minus. By the way, it's enough to work on the minus side because theta at 0 lives on the minus side. So it will kill the plus part anyway. I mean, I'm not. We actually compute this full fitting ideal. And it's the Synod-Kurihara ideal. Yeah. Now, this problem, the imprimitivity problem, so this is serious. We've been trying to eliminate, to get rid of the imprimitivity. Why is it serious? Because, for example, if SL contains a prime, say, that splits completely in my extension, then that kills the whole theta at 0. So you're not saying anything here. So Andrew Wiles designed a very clever technique that allows you to get rid of the imprimitivity under certain hypotheses. We've sort of refined a little bit that technique, and we can do more cases now, but we are not done eliminating it in general. And Florian is telling me that I should finish, and I will in 2 minutes. Theorem 2, cosine. So we get refined, but not imprimitive, just the clean cosine. Those of you who are familiar with special values at negative integers, you know that there are no extra zeros to be gained from SL inside S. So define cosine. So theta, same hypothesis, but no SL is inside S. So L is different from 2, mu L is 0. Then theta at 1 minus n is inside the fitting ideal over ZL bracket G of H2 et al. Of OKS 1 over L 0 for all n, which is, of course, inside the annihilator, which was the original formulation of cosine. Thank you.
We are not over one, but for 2 short questions. Yes.
I find it miraculous you can use the out of the ideal class group at the top, you're somehow getting a ZLG projective module.
Yeah, yeah.
It's absolutely.
Yeah. Let me tell you what else this leads to. So we heard so that is due to the fact that these extensions, if these extensions were split, you would never get a ZL bracket G projective module. So it's the way this part and this part, which we pretty much understand very well, are glued together in this ZL bracket G extension. That's, yeah. One other thing that this leads to, so we heard Henri Johnston talking about Tate sequences, for example. So those are special sequences inside some X2. There is a Tate class, and Tate proved in the 1960s that there is a special representative in this Tate class, given by some projective module. But we don't know how to construct canonically a sequence, a Tate sequence, that lives in the Tate class. So, or we didn't know up until a few months ago. We do now. We are now able to construct. So, for example, in function fields, the Tate sequence contains this module twice in the middle. We are having trouble proving that it actually lands in the Tate class all the time. Tate is involved in this project and very excited about it now. I mean, we have a geometric interpretation of a canonical representative for a Tate sequence.
Yeah.
Yeah.
Were you gonna say It's a short-term question. Is that in theorem 1? Is that the script G or capital G?
No, this is script. This is just capital G. It's ZL bracket G projective. If you want to know what happens over script G, it has projective dimension 1 over ZL double bracket script G. Yeah. Yeah. Because there are no finite lambda submodules in there.
But there's a finitely generating ZP module.
Absolutely. Yeah, absolutely. Yeah.
ZL.
Right. Yeah.
When you take the duals, so what happens when you explain us what is when you take the duals in your sexicon star, we know, so you have the torus part corresponds to lattice and so on. What is it?
The duals. We have a duality pairing, and it's needed. Unfortunately, we don't have a full duality pairing involving both S and T. We have a duality pairing which is more or less a Kummer-like pairing involving only S. That is needed in proving cosinus. There is no perfect analogy here. I understand what you're saying. So in function fields, you exchange the lattice with the torus and so forth. It's not happening here. It's not as good. But we do have a pairing between this motive, MS empty set, and M empty set S. And that's enough for cosinus. Cosinus only keeps track of S, not of T.